Lastly for today, we're going to talk about the force on current carrying wires. I should say that we have now jumped ahead a little bit in the book. This is section 32.8, and I have chosen to jump ahead. One, because we were just talking about forces, so we might as well do the other forces that we see. And also, we're going to use this in today's lab, so I wanted you guys to have seen it before we use it in lab. So just like how a charge feels a force in a magnetic field if it is moving, a current, which is a bunch of moving charges, also feels a force in a magnetic field. And the equation for this is as follows. Our force is equal to IL cross B. So I here is, of course, our current. L is the length of the segment that we are interested in. Sometimes this is the portion of the wire that is in the magnetic field. Sometimes maybe our wire is long, but only a magnetic field is for part of it. So this is the length of whatever wire segment is feeling the field. And lastly, our magnetic field, of course, is the field around our wire. So this is not the field created by this wire. This is not the field created by this wire that we're talking about. This is the field created by maybe some other wire or maybe some permanent magnet, depending on the situation. The direction of this L here is the same as the direction of the current. It's, you could kind of argue that this vector should actually be on the current variable. It should be I vector times this scalar length. It really doesn't matter. I think, the direction of this is in the direction that the current flows. So let's do a couple examples of this just for our cross product practice. So let's say we have a magnetic field that is into the board again, and I have a wire in it that is vertical and is carrying current I. So IL, this vector is up, B is into the board, so up cross into the board, up cross into the board gives me a force to the left on this wire. And this force is going to be spread out across each part of the wire that is in the magnetic field. We know that we can have a magnetic field that is created by a wire, and we know that if another wire feels that magnetic field, it is going to feel a force. So that means that two wires next to each other are going to feel a mutual force, maybe attraction, maybe repulsion, maybe it's off in some different direction. We'll have to figure it out. But now we do know enough to figure it out. Let's say we have two wires that are parallel, and we're only going to worry about parallel wires for this problem. You can do the calculations for wires at some oblique angle, and it can be harder, so we're not gonna sweat that. So let's say we have two wires. They are both length L. Maybe we're gonna imagine the currents just stop at the ends, although maybe these turn off in different directions or something like that. So this is length L. This wire has current going to the right that we will label I1. This wire has current I2. We'll say it's also going to the right. So we can do this in any order. I'm just going to pick a place to start. So I1 creates a magnetic field, and let's draw what that looks like. So for this, we put our thumb in the direction of this is the field of a wire. So to figure out what direction the field of a wire is in, we put our thumb in the direction of the current, and our fingers are wrapping around that wire in the direction the field is going. So that means above the wire, it is coming out of the board. And below the wire, it is going into the board. I've drawn these right close to this, but we know we're still going to get a magnetic field down here, right? Because we know that the strength of this magnetic field, B, is equal to mu naught I1 over 2 pi r, where r is the distance we are away from I1. If wire 2 is some distance, we'll call that d, away from wire I1, we know the magnetic field here at the location of I2 is going to be mu naught I1 over 2 pi d. So this is the magnetic field that I2 feels. This is the field generated by current 1 at the location of current 2. Now we know enough to figure out what the force is between them. So just in terms of direction, we have a current to the right, we have our magnetic field into the board. So I, L cross B gives me a force that is up on I2. And so the size of this force is equal to ILB sine theta, just from our cross product. I and B are at 90 degrees, so theta is just 90 degrees. So the sine of 90 degrees is just 1, so we don't have to worry about this. So if everything's at nice right angles, our force is just I times L times B, and we know what B is. Before I plug that in, I should say that if this is the force on I2, then the current in this equation is I2. So we have I2 times L times this field that current 2 is feeling from current 1, so that's mu naught I1 over 2 pi d. Rearranging this, we get the following. Mu naught I1 times I2 over 2 pi d, I forgot the L, times L. This is our equation for the magnitude of the force between two wires. I know we only solved it in one direction for the force on I2, but you could guess from Newton's third law that the force that I1 feels is going to be equal and opposite to this force. We can at least very easily show that the direction that I1 feels a force is correct also. So let's look at the force, let's look at the magnetic field created by I2. So that current is to the right. So I2 is going to make a field that is out of the board up here and into the board down here. So that's the magnetic field from I2. So up here at the location of I1, that field is also into the board. So we have IL cross B for current 1. So that's IL cross B. That's going to give us a force that is downward. So the force on current 1 is downward. For these parallel currents, our two wires are attracted to each other. This board is kind of a mess, so we've done enough derivation. Let's just write the facts that we know now. I'll leave the equation up here. So for two parallel wires, the force between them is given by this, where the two currents are I1 and I2. They feel an attractive force if the currents are in the same direction. They're going to feel a repulsive force if the currents are in opposite directions. I'm not going to show this, but you can show this yourself with the right-hand rule. So two wires like this, where one has current to the right and the other has current to the left, they are going to feel forces pushing them apart, and this is the basis for today's lab.